long after the outer layers of a massive star have been thrown into space. A smaller object remains at the center of the fading debris. It is no larger than a city, yet it holds more matter than the Sunday. Its surface has been pressed almost flat by gravity. Beneath that surface, atoms have lost the shapes they once had, and matter has entered a state that no laboratory on Earth can fully reproduce. Before the story moves closer to that silent remnant, take a moment to settle into the room around you. If this kind of slow science storytelling helps you rest, you can subscribe, leave a like, or share the video with someone who also enjoys falling asleep beside the quiet facts of space. You can also leave a comment with the place you are listening from and the local time there. Perhaps the room is already dark, perhaps a fan is turning somewhere nearby, or a small light is still glowing at the edge of the bed. Let the shoulders loosen, allow the breathing to become unhurried, and find a position that asks nothing more from the body. The universe will continue without effort. Stars will burn, cool, collapse, and circle one another whether anyone is awake to watch them or not. There is no need to hold every name or number. The images can pass slowly, one after another, while the night becomes quieter. At the center of an old supernova, the last heat is still leaving a sphere of matter compressed beyond ordinary experience. Around it, the expanding cloud grows thinner. Inside it, gravity has finished its work, and the long life of a neutron star is beginning. Before that beginning, there is a long period of burning. A massive star spends most of its life in a balance so steady that, from a great distance, it can appear almost permanent. Gravity pulls every layer inward. Heat and pressure push back. Between those two tendencies, the star holds its shape. Hydrogen fuses into helium in the central regions, and the energy released there moves outward through layers of gas until it reaches space as light. Nothing about the process is hurried. The star may remain in this state for millions of years, losing energy every second, while still seeming unchanged. The balance is not stillness, it is continuous work. Inside the core, particles meet under pressures that do not exist naturally on Earth. The temperature is high enough for atomic nuclei to overcome their electrical repulsion and join. Each successful fusion reaction releases a small amount of energy. Taken one reaction at a time, the change is almost nothing. Taken across the full volume of a stellar core, it becomes the pressure that keeps thousands of trillions of tons of matter from falling inward. Hydrogen does not last forever. As it becomes scarce in the center, the pattern of the star changes. The core contracts slightly, heating as it does, while the outer layers expand. Helium begins to fuse into carbon and oxygen. Later, in stars born with enough mass, the sequence continues. Carbon burns, neon follows, oxygen and silicon take their turns. Each stage is shorter than the one before it, because the reactions demand higher temperatures and release energy through faster, less efficient route. The star begins to resemble a set of shells nested inside one another. Different fuels burn at different depths. Hydrogen remains active farther out. Helium burns beneath it. Deeper still, heavier nuclei are formed in zones that would be impossible to separate by any visible boundary. There are no hard walls inside the star, only gradients of temperature, density, and composition, with matter flowing slowly between them. Near the center, silicon fusion builds a core, dominated by iron group nuclei. This is where the long resistance to gravity begins to fail. Iron can be rearranged into heavier nuclei, but doing so does not release the energy needed to support the star. The core still grows as material from the burning layers above settles inward, yet the source of pressure that once held the central regions open is reaching its limit. For a time, the core is supported by a quantum effect rather than ordinary heat. Electrons are forced into an extremely crowded state, and the rules of quantum mechanics prevent all of them from occupying the same conditions at once. This resistance is called electron degeneracy pressure. It does not depend on the core remaining hot in the same way gas pressure does. It can hold dense matter against gravity, but only up to a point. That point arrives quietly. There is no warning visible from the surface that matches the speed of what is happening below. The core gains mass, its density rises, temperatures climb into the billions of degrees. High-energy photons begin breaking iron nuclei apart, consuming energy rather than releasing it. Electrons are pressed into protons, producing neutrons and neutrinos. Both processes remove support from the core at nearly the same time. Gravity no longer meets an equal response. The collapse begins across a region larger than any city and finishes in less than a second. Matter that had been resting in a dense but ordered state starts moving inward at a large fraction of the speed of light. The inner core falls almost together, while layers above it follow. Distances shrink so quickly that the idea of a stable surface disappears. The central material is not simply compressed in the ordinary sense. Its particles are forced into a new arrangement under a pressure that changes the identity of the matter itself. Electrons and protons combine. Neutrons become dominant. Neutrinos pour outward from the reactions, though most of them do not escape immediately. Even these nearly massless particles, which pass through planets with little resistance, find the collapsing core dense enough to slow them. For a brief interval, energy is trapped inside matter that is becoming smaller by the millisecond. The inward motion does not continue without limit. As the central density approaches that found inside atomic nuclei, the behavior of the material changes again. Neutrons resist being packed into the same states. The strong nuclear force, which acts across tiny distances, also begins to oppose further compression. The inner core stiffens. The collapse meets resistance. Material still falling from above strikes the newly hardened center. The inner core rebounds slightly, sending a pressure wave outward. Early descriptions of supernovae often treated this rebound as the main cause of the explosion, but the full process is more difficult. The outward-moving shock loses energy as it breaks apart heavy nuclei and moves through dense infalling matter. It slows. For a short time, it can appear that the star may collapse without producing the bright explosion expected at the surface. The neutrinos alter that outcome. An enormous number of them are released as the core changes from electron-rich matter into neutron-rich matter. Most carry energy away, but a small fraction deposit energy behind the stalled shock. Convection and turbulent motion help the heating become uneven. The shock is stirred, revived, and pushed outward through the star. The exact details vary with the mass, rotation, and internal structure of the parent star, and models continue to improve, but the broad picture is clear. The explosion is powered not by burning alone, but by gravity, nuclear physics, and a flood of neutrinos moving through the collapsing core. The outer layers begin to leave. Gas that had remained bound to the star for millions of years is accelerated outward. Elements formed during the star's lifetime are carried into space. New nuclei are created in the heat of the explosion and in the flows of particles that pass through the expanding debris. The surface brightens only after events in the center have already transformed the object. By the time light from the explosion becomes visible, the core has completed most of its collapse. From the outside, the supernova is the most obvious part. It can outshine a galaxy for a short period. Its expanding shell catches the surrounding gas and heats it. Over years, decades, and centuries, the debris spreads into a widening cloud. Filaments form. Knots of oxygen, silicon, sulfur, and iron move at different speeds. Radio waves and X-rays arise, where the ejected material collides with the space around it. At the center, something much smaller remains. The surviving core may contain more mass than the Sun, while measuring only about 20 kilometers across. The exact size depends on the equation of state, the still uncertain relationship between pressure and density in matter, compressed beyond atomic form. Even without that final answer, the scale is already difficult to place beside anything familiar. A journey across the object would cover the distance between two nearby towns. The mass being crossed would belong to a star. The formation of this remnant is not guaranteed every time a star dies. Lower mass stars do not reach the sequence of burning stages required for core collapse. They shed their outer layers more gently and leave behind white dwarfs. At the other end, some collapsing cores are too massive to settle as neutron stars. Gravity continues past the point at which neutron pressure can support the material, and a black hole forms. Between those outcomes lies a narrow and important range. The mass of the star at birth matters, but it is not the only factor. Massive stars lose material through winds. They may exchange gas with a companion. Their cores rotate at different rates. Their chemical composition changes how efficiently they burn and how much mass remains at the end. Two stars born with similar masses can follow different paths because their lives are shaped by different surroundings. The remnant itself may also gain or lose enough matter during the explosion to change its fate. Some material launched outward does not escape. It slows, turns, and falls back toward the center. If enough returns, a neutron star that formed briefly may later collapse into a black hole. In other cases, the explosion removes the outer layers efficiently and leaves a stable, compact object behind. Stable does not mean ordinary. The newborn neutron star is extremely hot. Its interior temperature can reach hundreds of billions of degrees immediately after collapse, though it cools rapidly by emitting neutrinos. Most of that cooling cannot be seen directly. The surface remains far hotter than any planetary crust, but the deeper interior loses energy through particles that travel outward from regions hidden beneath the star's thin atmosphere. The object may also be moving. A supernova is rarely perfectly symmetrical. If more material is expelled in one direction than another, the compact remnant receives a recoil. Some neutron stars leave their birthplaces at hundreds of kilometers per second. They cross the expanding debris and continue into the galaxy, carrying their rotation and magnetic field through interstellar space. A star that once occupied millions of kilometers has become a dark point moving between other stars. The direction of that motion can preserve a faint memory of the explosion. So can the surrounding remnant. Astronomers study the shapes of supernova debris, the distribution of elements, and the position of the compact object to reconstruct a collapse that cannot be observed from inside. The evidence arrives in layers: light from hot gas, radio emission from charged particles, X-rays from shock, heated material, and sometimes a pulsating signal from the core. The transformation is nearly complete by then. What remains is no longer sustained by fusion. There is no central flame replacing one fuel with another. The neutron star shines because it is hot, because particles move through its magnetic field, and because rotation can power radiation. Its future is governed by cooling, magnetic change, and the slow loss of rotational energy. The active life of the parent star has ended, but the remnant is not inert. This difference matters. A dead star is not dead matter. The phrase is useful only because nuclear burning has stopped. On smaller scales, the object remains full of motion. The crust adjusts as the star cools. Magnetic fields shift through matter that conducts electricity with very little resistance. Superfluid regions inside can move differently from the solid layers above them. The surface releases heat left from formation, while charged particles are guided along magnetic paths beyond the atmosphere. None of this is visible in the way a normal star is visible. A neutron star is too small to appear as a disk through an ordinary telescope. Its presence is inferred through effects: regular pulses, X-ray hotspots, the motion of a companion, or the expanding cloud that marks the place where a massive star once stood. The contrast between the cloud and the core is one of scale. The supernova remnant grows larger every year, becoming light and thin as it spreads. The neutron star remains compact, holding almost the same mass inside almost the same radius. One part of the event becomes a structure measured in light years. The other can fit inside a region that a car might cross in less than half an hour. Time treats them differently as well. The debris changes visibly across human generations. Shock fronts slow, filaments fade, dust cools and mixes with the surrounding medium. The neutron star can persist for billions of years, unless it meets a companion or gains enough mass to collapse further. Its surface temperature falls. Its spin becomes slower. The strong field near it may weaken or rearrange, yet the compact form remains. The parent star once held itself open by releasing energy. The remnant endures because matter has reached a condition in which gravity is resisted by quantum rules and nuclear forces. The first balance belongs to a burning gas. The second belongs to matter pressed close to its limit. There is no sharp moment when one identity becomes the other in any human sense. The collapse takes less than a second, but it contains several physical transitions. The iron core loses support. Neutrinos become trapped and then escape. Nuclear density is reached. The shock moves outward. The star's layers separate from the center. Each stage overlaps the next. From far away, the event is a burst of light. Closer in, it is a change of state. The expanding material carries the history of the star outward. Carbon, oxygen, silicon, and iron join the wider galaxy. Some of that matter may later enter clouds where new stars form. The compact core keeps a different record. Its mass, spin, motion, temperature, and magnetic field preserve information about the final seconds of collapse. That record is incomplete. The star's interior cannot be opened or sampled. Models begin with physical laws tested on Earth, then extend them into pressures far beyond any laboratory. Observations place limits on what can be true. A remnant of a certain mass cannot have every possible radius. A cooling surface cannot follow every theoretical path. A measured spin cannot come from every collapse scenario. Slowly, the allowed possibilities narrow. The first part of the neutron-star's story is therefore not only about an ending. It is about how matter responds when the long support of stellar burning is removed. Gravity acts first, drawing the core inward. Quantum resistance answers. Nuclear forces answer after that. The result is a body balanced at a density close to the density of an atomic nucleus, suspended between the ordinary life of a star and the deeper collapse of a black hole. Around it, the supernova continues to expand. The brightest light moves away. The gas cools. The central object becomes harder to see against the growing dark. It is smaller than the cloud by an almost absurd degree, yet it holds the part of the star that underwent the greatest change. The remaining heat leaves slowly through the surface. The magnetic field reaches into space. Rotation continues because there is almost nothing to stop it. A star has lost its outer form. A neutron star has taken its place. A neutron star has taken its place. Seen from a distance, it may appear almost featureless, a small point of heat against the much larger cloud left by the explosion. Nothing about that faint point suggests the amount of matter held inside it. The radius is measured in kilometers. The mass is measured in suns. Those two scales do not usually belong together. On Earth, cities spread outward across valleys, rivers, coastlines, and plains. A neutron star occupies a comparable width, yet the matter inside it was once distributed through the core of a giant star. The collapse has not simply reduced the empty spaces between atoms. It has changed the atoms themselves. Under the rising pressure, electrons are driven into protons, and the distinction between ordinary atomic matter and the material inside the remnant begins to fade. The word dense is not quite enough. Ordinary solids feel firm because their atoms resist being pushed closer together. Even in metal or stone, most of each atom is not filled with material in the way familiar objects suggest. A small nucleus sits at the center, surrounded by electrons whose behavior is described by probability rather than tiny planetary paths. In a neutron star, gravity removes much of that arrangement. Matter is forced into conditions closer to those inside an atomic nucleus than to anything found in a mountain, an ocean, or a human body. A small volume would contain more mass than any ordinary comparison can hold comfortably. The common image of a teaspoon weighing as much as a mountain is useful, though it remains only a translation into human scale. No spoon could reach the surface, remain intact, collect the material, or lift it away. The comparison is not a practical possibility. It is a way of showing how completely the old structure of matter has been compressed. The outermost region is not bare in the usual sense. A neutron star can possess a very thin atmosphere, perhaps only centimeters thick, made of light elements such as hydrogen or helium, if those elements remain available. Beneath it lies a surface that is solid, though the word surface hides how unusual the conditions are. The crust is a lattice of atomic nuclei, immersed in a sea of electrons, all held under pressures that increase rapidly with depth. The surface gravity shapes everything above it. A person standing on such an object is not a physical scenario that can occur, but the imagined comparison helps reveal the strength of the field. The pull is roughly 100 billion times stronger than gravity at Earth's surface, depending on the star's mass and radius. A small change in height produces a large change in gravitational energy. Matter arriving from space is accelerated to a significant fraction of the speed of light before it reaches the crust. The effect is not merely weight. Gravity also changes time and light. Close to the surface, clocks would run more slowly, relative to clocks far away. Light climbing out of the gravitational field loses energy, shifting toward longer wavelengths. This gravitational redshift is one reason observations of the surface can reveal information about the star's mass and radius. The photons leave the crust carrying a faint imprint of the space-time through which they have climbed. The star also bends their paths. On an ordinary sphere, only the side facing an observer should be visible. Around a neutron star, the gravitational field curves light strongly enough that part of the far side can come into view. A hot region rotating out of sight may remain visible for longer than simple geometry would predict. The object can reveal more than half of its surface at once, not because it is transparent, but because the light travels along curved routes. This bending softens the rise and fall of X-ray pulses from hot spots. It also allows astronomers to estimate the compactness of the star. A smaller radius for the same mass produces stronger bending. A larger radius produces less. The light curve becomes a measurement of gravity, written in repeating brightness. The surface itself is remarkably smooth on large scales. Strong gravity pulls material toward the lowest available level, reducing the height of mountains that could exist on the crust. That does not mean the star is perfectly round. Rotation can widen the equator slightly. Magnetic stress can deform the crust. Small irregularities may remain, and even a tiny distortion matters when so much mass is rotating. The largest possible mountain is not known with complete certainty because it depends on the strength and composition of the crust. It may rise only centimeters, perhaps somewhat more under certain conditions. On Earth, such a change would be too small to call a mountain. On a neutron star, it can alter the distribution of mass enough to influence the gravitational waves produced by rotation. A surface so smooth can still be restless. The crust cools after formation. It contracts. Magnetic forces press and pull through it. In some neutron stars, material from a companion falls onto the surface and adds new layers. The crust can crack or shift when stress becomes too great, though the event is not identical to an earthquake. The material is denser, the forces are different, and the surrounding magnetic field can carry the disturbance outward. The solid exterior is only a thin fraction of the star's radius. Beneath it, matter no longer resembles a conventional crystal. The nuclei become increasingly rich in neutrons, as pressure forces more electrons into protons. Eventually, neutrons begin to escape the nuclei and move through the lattice. This region is sometimes called the inner crust. The transition is gradual. At shallower depths, nuclei remain roughly spherical. Deeper down, the competition between nuclear attraction and electrical repulsion may shape them into rods, sheets, and more complex structures. These theoretical forms are often called nuclear pasta because their geometry resembles strands, layers, or tubes. The name is playful, the physics is not. These structures may affect how heat and electrical currents move through the crust. No instrument has directly photographed them. Their existence comes from models of matter under extreme density. Different calculations produce different details, but the broad idea follows from known forces acting in an unfamiliar balance. The nuclei are crowded so closely that their shapes can no longer remain isolated. Heat moves outward through these layers. A newborn neutron star begins with an interior far hotter than its surface. Neutrinos carry away much of the energy during the early stages. Later, thermal energy flows through the crust and escapes as X-rays. The cooling rate depends on what particles and reactions are present inside. A star that cools quickly may allow neutrino-producing processes that a slower cooling star does not. This turns temperature into evidence. Astronomers cannot drill into the crust, but they can watch how the surface changes with time. In systems where a neutron star pulls matter from a companion, periods of accretion can heat the crust. When the inflow stops, the crust cools back toward equilibrium with the interior. The decline in X-ray brightness provides clues about thermal conductivity, impurities, and the thickness of the crust. A neutron star is therefore measured by patience. Some observations last seconds and record rapid pulses. Others continue for years, following a slow cooling curve. The object reveals different properties on different timescales. A hot spot crossing the visible face speaks about rotation and light bending. A cooling surface speaks about heat transport. A sudden change in spin may speak about motion beneath the crust. Even the atmosphere changes what the surface appears to be. Hydrogen, helium, carbon, or heavier elements absorb and re-emit radiation in different ways. A surface temperature inferred from a simple blackbody model can be misleading if the atmosphere is ignored. The magnetic field also changes how radiation moves through the gas, making the emitted light depend on direction and polarization. The star does not shine evenly. Magnetic fields guide charged particles toward certain regions, often near the magnetic poles. These areas can become hotter than the rest of the surface. As the star rotates, the hot spots move in and out of view, producing pulses in X-rays. The pulses are shaped by the spot size, the field geometry, the atmosphere, the star's rotation, and the bending of light. A pulse is not only a flash, it is a map folded into time. Each rise and fall in brightness contains information about a surface too small and too distant to resolve directly. The signal may look simple, but the model behind it must account for gravity, heat, geometry, and radiation. Measurements from instruments such as NICER use this approach to place limits on the masses and radii of selected pulsars. Mass can sometimes be measured through orbital motion. Radius is harder. Together, they are especially valuable because the relationship between them depends on the behavior of matter at high density. A neutron star with a known mass but a larger radius would imply that the interior matter resists compression more strongly. A smaller radius would imply a softer response. That answer lies deeper than the crust. For now, the surface provides only indirect access. It is the place where interior heat becomes light, where magnetic fields emerge, and where infalling matter releases energy. The crust stands between the visible universe and a core that cannot be seen. When matter falls onto the surface from a companion star, the release of gravitational energy can be intense. Gas drawn from the companion forms a disk, spirals inward, and heats as it loses orbital energy. Near the neutron star, the magnetic field may channel the flow onto small regions. The impact heats the surface and creates bright X-ray emission. In some systems, fresh hydrogen and helium accumulate on the crust. Pressure and temperature rise until nuclear burning becomes unstable. A thermonuclear X-ray burst follows, spreading across the surface within seconds. The light then fades as the layer cools. These bursts are not explosions of the entire star. They are thin surface events, small in mass but bright enough to be observed across the galaxy. Their repetition reveals the rate at which matter is arriving. Their spectra can carry signs of temperature, gravity, and atmospheric composition. In rare cases, the radiation becomes strong enough to lift the outer layers of the atmosphere temporarily before they settle again. The surface remains bound. Escape requires a large fraction of the speed of light. Even particles heated to enormous temperatures find the gravitational field difficult to leave. The escape speed depends on the star's compactness and can approach more than half the speed of light. This does not mean the surface is a black hole. Light still escapes. There is no event horizon. Yet the margin between the object and further collapse is narrow compared with ordinary stars. That distinction defines much of neutron-star physics. A white dwarf is supported mainly by electron degeneracy pressure and has a radius comparable to Earth. A neutron star is supported by forces acting at nuclear density and is hundreds of times smaller. A black hole has crossed the point at which no known pressure can halt collapse. The neutron star occupies the space between them, not only in size, but in physical law. Its mass cannot grow without limit. Observations have found neutron stars with masses around twice that of the Sunday. Their existence rules out models of dense matter that would collapse under smaller loads. There must be enough pressure inside to support them. At some higher mass, support fails, and a black hole forms. The exact maximum remains uncertain because it depends on the same equation of state that governs the radius. The surface gives hints, but never the full answer. Strong magnetic fields complicate the picture further. In ordinary laboratory materials, atoms keep familiar shapes. Near the strongest neutron star fields, electron motion is confined, and atomic structure becomes elongated along magnetic lines. Radiation travels differently depending on its polarization. The vacuum itself can behave like a material, altering the passage of light through a quantum effect known as vacuum birefringence. This is not a property visible to the eye. It appears in the orientation of light waves and in the way different modes of radiation move through the magnetic environment. Observations of polarization may therefore offer another route into the physics of the surface and field. The object is small, but every layer changes the signal. An atmosphere only a few centimeters thick alters the spectrum. A crust about a kilometer deep stores stress and carries heat. A slight bulge changes rotation. A hot spot smaller than a continent shapes an X-ray pulse that crosses thousands of light years. The distances are large. The structures producing the signal are not. Scale turns inward here. The star does not need a broad landscape to contain complexity. It holds complexity vertically, through pressure. A short descent through the outer layers passes from gas to crystal, from nuclei to neutron-rich matter, and from forms that resemble atoms to forms that do not. The surface is the final place where familiar matter still has a partial foothold. Below it, the old divisions become less useful. Nuclei lose their clear boundaries. Neutrons move between them. Deeper still, the density approaches and then exceeds that of atomic nuclei. The words solid and liquid begin to require new meanings. The material may flow without viscosity and conduct electricity without resistance. The boundary is not a clean line that could be marked on a diagram without qualification. It is a range over which one description of matter loses usefulness and another begins. Density rises continuously, while the particles respond in stages. The crust does not end like rock above an ocean. It thins into a different phase, and the star becomes less like a solid body resting on a fluid than a single connected system with several ways of moving. The next part of the journey does not move outward into space. It moves down. The crust grows darker, hotter, and denser with depth. The lattice changes shape. Free neutrons collect between nuclei. Heat passes through a structure no laboratory can build and no telescope can resolve. At the base of the crust, the ordered surface world gives way to a fluid interior. There, the neutron star keeps its deepest uncertainties. There, the neutron star keeps its deepest uncertainties. Below the crust, pressure has erased nearly every feature that would make matter familiar. The ordered lattice of nuclei gives way to a region where neutrons move with far greater freedom, no longer confined to individual atoms. Gravity has carried the star beyond the structures that define ordinary solids, yet the interior is not a simple sea of identical particles. It is layered, responsive, and still only partly understood. The first change is subtle in language and enormous in physics. Neutrons begin to behave collectively. Under the right conditions, many of them occupy a shared quantum state and form a superfluid, a substance that can move with almost no internal friction. Superfluid helium can be produced in laboratories at very low temperatures, where it climbs container walls and flows through spaces that ordinary liquids cannot cross. Inside a neutron star, the temperature is high by terrestrial standards, but the density is so great that pairing between particles can still create a related state. The comparison is useful only up to a point. The interior is not a cold laboratory fluid resting in a glass vessel. It is matter under nuclear pressure, threaded by magnetic fields and contained by gravity. Still, the word superfluid captures an important possibility. Part of the star can move differently from the crust above it. That difference may become visible when the star changes its spin. Some pulsars rotate with extraordinary regularity, then suddenly speed up by a tiny amount. These events are called glitches. The change may be only a small fraction of the rotation rate, but it arrives abruptly against an otherwise steady rhythm. One explanation is that a superfluid inside the star stores angular momentum, while the crust gradually slows. When vortices in the superfluid shift or detach from the crustal lattice, some of that stored motion is transferred outward. The star adjusts in a moment. Afterward, the rotation may settle slowly toward its earlier pattern. The exact behavior differs from one pulsar to another, suggesting that several regions and processes may be involved. Glitches do not provide a direct image of the interior, but they show that the layers are not locked together as a single rigid body. Something beneath the crust can lag behind, hold motion, and release it. A rotating superfluid does not turn in the same way as a solid sphere. Its motion is organized into thin quantum vortices, each carrying a fixed amount of circulation. These vortices form an array through the fluid. As the neutron star loses rotational energy, the vortices must move outward so that the superfluid can slow. If they become pinned to structures in the crust, the smooth adjustment is interrupted. Stress gathers without sound. The pinning cannot last forever. Vortices move, perhaps in groups, and the crust receives a small transfer of angular momentum. The result is measured across light years as a change in pulse arrival time. A process taking place in a region no telescope can see leaves a mark in the timing of radiation reaching Earth. This is one of the quiet strengths of pulsar astronomy. The interior is inaccessible, but its motion is not completely hidden. Neutrons may not be the only particles forming paired states. Protons, though fewer in number, may become superconducting. In an electrical superconductor, current can flow without ordinary resistance. Inside a neutron star, proton superconductivity may shape the way magnetic fields pass through the core. Rather than spreading smoothly, magnetic flux may be divided into narrow tubes, each carrying a fixed amount of field. The superfluid vortices and magnetic flux tubes may interact. That interaction could influence glitches, long-term magnetic evolution, and the coupling between the crust and core. Yet the details depend on the state of matter at densities that cannot be recreated fully in experiments. The calculations become sensitive to how particles interact under pressure, and small differences in assumptions lead to different pictures of the interior. No single model has closed the question. The deeper core may contain mostly neutrons, with a smaller population of protons, electrons, and perhaps muons. Muons are heavier relatives of electrons. They can appear when the energy of the matter becomes high enough for their creation to reduce the overall energy of the system. Their presence changes the balance of charge and may open additional routes for cooling. Farther inward, the possibilities widen. Some models allow strange particles called hyperons to appear. These contain strange quarks, one of the fundamental particle types not normally present in stable atomic nuclei. Other models suggest that the boundaries between neutrons and protons may dissolve, creating regions of deconfined quark matter. In that state, quarks would no longer remain bound in groups of 3 inside individual nucleons. There may be mixed phases. There may be transitions that occur gradually rather than sharply. There may be forms of matter not yet described with confidence. The honest answer is that the central composition is unknown. This uncertainty is not a gap caused by carelessness. It comes from the limits of experiment and observation. Atomic nuclei can be studied in laboratories, and collisions between heavy ions can briefly create dense matter. Those experiments reveal important features of the strong nuclear force, but they do not reproduce the cold, neutron-rich, gravitationally confined material inside an old neutron star. The conditions overlap only partly. To connect them, physicists use an equation of state. The name sounds formal, but the idea is simple. An equation of state describes how strongly matter pushes back when it is compressed. It relates quantities such as pressure, density, temperature, and composition. For neutron stars, the most important question is how pressure rises as density increases beyond that found in an atomic nucleus. A stiffer equation of state produces greater pressure at a given density. That pressure can support a larger radius for the same mass. A softer equation of state allows matter to compress more, producing a smaller star. If the material becomes too soft, it cannot support the most massive neutron stars already observed. Mass and radius, therefore, become clues to the invisible core. A measurement of mass alone rules out some possibilities. A measurement of radius narrows the range further. Several accurate measurements across stars of different masses can begin to outline the pressure of matter at different depths. No single object gives the whole answer, but each one removes part of the uncertainty. This is why a small change in radius matters. The measurements are difficult because neutron stars are distant and small. Their surfaces cannot be resolved directly as ordinary images. Astronomers instead study X-ray pulses from rotating hotspots. The shape of each pulse depends on the star's compactness, the size and position of the hot regions, the viewing angle, and the way light bends around the surface. The information arrives mixed together. A model must separate geometry from gravity and atmosphere from temperature. It must account for how the star rotates and how radiation leaves a magnetized surface. Many possible combinations can produce similar signals, so the observations are repeated and compared across long periods. NICER, an X-ray instrument operating from the International Space Station, was built in part for this work. It records the arrival times and energies of individual X-ray photons from pulsars. By following the changing brightness as hotspots rotate across the visible face, it helps place limits on stellar mass and radius. The instrument does not see through the crust. It measures light that has already completed the journey outward. The value comes from how that light has been shaped. Gravity bends the path. Rotation changes the timing. The atmosphere changes the spectrum. The pulse profile carries all of these influences at once. From that pattern, researchers infer which stars are slightly wider and which are more compact. The results remain ranges rather than perfect values, but the ranges are narrow enough to challenge some theories of dense matter. Other observations add different constraints. When two neutron stars orbit one another, their masses can be measured through precise timing. When they spiral together, the gravitational wave signal depends on how easily each star is deformed by the gravity of its companion. This property is called tidal deformability. A larger, less compact star is stretched more. A smaller, denser star resists the tidal field differently. The effect is tiny until the final stages of the orbit, yet the signal carries it. The waves passing through detectors on Earth include information about the internal response of both stars. A merger that lasts only seconds in the sensitive frequency range can therefore speak about matter hidden for billions of years. Cooling provides another path. A neutron star loses heat through neutrino emission from the interior and through photons from the surface. Different particles and phases allow different neutrino reactions. Some processes release energy rapidly. Others are slower. Observing how temperature changes with age can help distinguish between them, though age and surface composition are not always known precisely. A young neutron star, may cool quickly at first, then more gradually. Superfluidity can suppress some reactions while enabling others. Pairing itself can release neutrinos as particles enter the superfluid state. The cooling curve becomes a record of transitions occurring far beneath the surface. Once again, the evidence is indirect. The core remains still in appearance and active in detail. Pressure increases toward the center. Density may reach several times that of an atomic nucleus. The distinction between separate particles may become blurred by interactions. Superfluid regions rotate through vortices. Superconducting regions guide magnetic flux. Neutrinos carry energy away from reactions too deep for light to reach directly. The star can seem simple from outside. A sphere, a pulse, a point of X-rays. Inside, it is a sequence of phases layered by gravity. The boundaries may not remain fixed. The phrase neutron-star may hide several kinds of interior. Some may contain only neutrons, protons, electrons, and muons in their deepest regions. Others may include hyperons. Still others may contain quark matter. A phase transition could create a dense inner core separated from the outer core by a change in compressibility. Under certain models, two stars with the same mass might even exist with different radii, because their interiors belong to different stable configurations. These possibilities are not established facts. They are allowed outcomes within some theories. The task is to find which possibilities nature has chosen. Heavy neutron stars already tell part of the story. Any equation of state must support them without collapsing. Merger observations tell another part by limiting how easily stars deform. X-ray pulse modeling adds radius information. Nuclear experiments constrain the behavior of particles at lower densities. Each method touches a different edge of the same unknown region. The answers must agree. A model that fits one observation but fails another cannot describe the whole star. This is why progress is slow and cumulative. No single detection opens the core. Instead, different forms of evidence press inward from several directions. The interior itself remains beyond direct reach. There is no exposed piece of neutron star matter drifting nearby. If a fragment could somehow be removed from the gravitational pressure holding it together, it would not remain in the same state. The dense arrangement exists because the entire star confines it. Once released, the material would expand and transform. The core cannot be sampled without changing the sample. This makes the star unlike a planet, where rocks can be collected, or an atmosphere, where gases can be analyzed locally. Its deepest matter is inseparable from the gravity creating it. The object is both container and experiment. Even the idea of a central point is less simple than it appears. Pressure is greatest there, but rotation can alter the distribution of density. A rapidly spinning star becomes slightly wider at the equator. In the fastest objects, rotation provides additional support against gravity, allowing a mass that might collapse if the spin slowed. As rotational energy is lost, that support decreases. A very massive neutron star formed in a merger may survive for a short time because it rotates rapidly or because different layers rotate at different rates. When the rotation becomes more uniform and slows, collapse may follow. The final state can depend not only on mass, but on timing. The interior is therefore connected to the star's future. Its pressure decides whether it remains stable. Its superfluid motion affects glitches. Its superconducting regions shape magnetic evolution. Its cooling reveals particle reactions. Its deformability changes the waves produced in a merger. What appears to be hidden influences nearly every signal the star sends outward. The crust is only the visible threshold. Below it lies matter moving without ordinary friction, currents flowing with almost no resistance, and particles arranged by forces that dominate only at tiny scales. The star remains calm in shape, while its interior supports several kinds of motion at once. The core keeps its details. Astronomers continue to measure the surface, timing, mass, temperature, and gravitational influence. Each observation narrows the range of possible interiors. Some models disappear, Others survive. New ones are built when the evidence demands a different balance between pressure and density. The mystery becomes smaller, without becoming simple. At the edge of the core, neutron-rich matter flows beneath a solid crust. Deeper down, protons and neutrons may pair. Farther inward, the identities of the particles may change. At the center, several theories remain possible, each consistent with part of what is known. The star does not reveal which one by sight. It reveals itself through rhythm. A tiny jump in spin suggests movement between layers. A pulse profile suggests a radius. A cooling curve suggests which reactions are open. A gravitational wave suggests how the whole body yields under tidal force. The interior writes its presence into time, temperature, and motion. Those signals travel outward from a place where ordinary atoms no longer exist. Beyond the surface, the magnetic field turns with the star. Charged particles follow it. Radiation is guided into beams that sweep through space. The hidden interior controls the rotation beneath them, and the rotation gives the distant object a voice. The next part of the journey returns to that voice. The next part of the journey returns to that voice. A neutron star may be silent to the eye and still keep time with extraordinary precision. Its rotation carries the magnetic field around with it, and the magnetic field shapes the motion of charged particles above the surface. Radiation leaves along preferred directions rather than spreading evenly. When one of those directions crosses the line of sight to Earth, a pulse arrives. Then another follows. The pattern can be so regular that the object appears less like a star and more like a clock hidden in space. Some pulsars rotate once every few seconds. Others turn dozens or hundreds of times in that same interval. The fastest known examples complete more than 700 rotations each second, their surfaces moving at a large fraction of the speed of light near the equator. The rotation begins before the neutron star exists. A massive star already turns during its ordinary life. When the core collapses, the same angular momentum is carried into a much smaller body. The effect resembles a spinning figure drawing in extended arms, though the scale and the physics are far removed from anything human. As the radius shrinks, the rotation speeds up. The magnetic field is compressed as well. Field lines that once passed through a much larger volume are drawn into a smaller region. Rotation and fluid motion during collapse can strengthen them further. The magnetic axis may tilt away from the rotation axis, so the regions where particles are accelerated do not remain fixed in one direction. They sweep. This creates the familiar lighthouse image. A lighthouse does not flash because its lamp turns on and off. It appears to flash because a narrow beam moves across a distant observer. A pulsar behaves in a related way. The radiation can be steady along the magnetic directions, yet it reaches Earth only when one of those directions points toward the solar system. The pulse is therefore a matter of alignment. Many neutron stars may produce beams that never cross Earth. They remain unseen as pulsars, even though they rotate and radiate. Others may point toward Earth for a time, and later move out of view as the rotation axis slowly changes. What is detected is only the fraction whose geometry allows the signal to arrive. The first pulsars were found through radio observations in the late 1960s. Their pulses were so evenly spaced that the signal did not resemble any known natural source. For a brief time, the possibility of an artificial origin had to be considered. The idea did not last. More examples appeared in different parts of the sky, with different pulse periods and the same broad behavior. The regularity does not come from machinery. It comes from inertia. A neutron star contains enormous mass in a very small volume. Changing its rotation requires energy. In empty space, with little friction acting from outside, the spin can continue for a very long time. The pulses remain regular because the body itself is difficult to disturb. Even so, the timing is not perfect. Most pulsars slow gradually. They lose rotational energy through electromagnetic radiation, particle winds, and the torque exerted by their magnetic fields. The change may be tiny from one rotation to the next, but over years it can be measured. A pulsar that spins hundreds of times each second will not keep exactly the same period forever. This slow loss of motion powers much of what is seen. Charged particles are pulled from the surface or created in the strong electric fields above it. They race along magnetic lines and emit radiation. Some move outward as a wind, carrying energy into the surrounding space. Where that wind meets gas left by the supernova, a glowing nebula can form. The Crab pulsar offers a clear example. It sits within the expanding debris of a supernova observed from Earth nearly 1,000 years ago. The pulsar turns about 30 times each second. Its wind fills the central region of the Crab Nebula with high-energy particles, producing light from radio wavelengths through X-rays. The star is smaller than a city, while the nebula around it stretches across several light-years. The pulses from a single pulsar do not all look alike. Radio, optical, X-ray, and gamma-ray pulses can arrive at slightly different phases because they are produced in different regions above the surface. Some profiles have one broad peak, others show two or more narrow peaks. The shape changes with wavelength. This variation contains geometry. It suggests where particles are accelerated and where the radiation originates. The magnetic poles may not be simple circular caps. The outer magnetosphere, far above the surface, can contribute much of the high-energy emission. Models must follow particles through curved fields while accounting for rapid rotation. The magnetosphere extends outward until a special distance where co-rotation would require motion at the speed of light. This boundary is called the light cylinder. Inside it, the magnetic field is tied closely to the turning star. Near and beyond it, the field opens and particles escape. For a pulsar rotating once every second, the light cylinder lies tens of thousands of kilometers from the surface. For a millisecond pulsar, it is much closer. The entire system, from crust to outer magnetic field, is shaped by the rotation period. Some pulsars begin slowly and become slower. Others are spun up later in life. A neutron-star in a binary system may draw gas from a companion. The gas forms a disk and spirals inward, carrying angular momentum. Over millions of years, the transfer can accelerate the neutron-star until it turns hundreds of times each second. These recycled pulsars are often called millisecond pulsars. Their speed is not simply left over from birth. It has been restored. The companion may eventually become a white dwarf, leaving the fast pulsar in a wide, stable orbit. Such systems are especially useful for timing because the pulses can remain regular across long intervals. Small changes in arrival time reveal the orbit, the motion of the system through the galaxy, and effects predicted by general relativity. A pulsar clock is never observed in isolation. Earth moves around the Sunday. The solar system moves through the galaxy. Interstellar plasma delays lower-frequency radio waves more than higher-frequency ones. Each influence must be corrected before the true rhythm of the star can be measured. Once those corrections are made, the remaining precision becomes powerful. Networks of millisecond pulsars are used to search for extremely long gravitational waves, with periods measured in years rather than seconds. A passing wave slightly changes the distance between Earth and each pulsar. The effect is very small, but a shared pattern across many pulsars can reveal a background produced by massive black hole binaries. Neutron stars become detectors by keeping time. The same regularity has also revealed planets through tiny variations in pulse arrival times. The first confirmed planets outside the solar system were found around a pulsar, an unexpected place to find worlds. The regular clock sometimes slips. A glitch causes a sudden increase in rotation, followed by a period of recovery. The hidden superfluid and the crust may exchange angular momentum. The timing event becomes a brief view into the interior, linking the pulse outside the star with motion beneath the surface. Other irregularities come from the magnetic environment. Some pulsars switch between emission states. Their pulses may weaken, disappear, or return. The change can be accompanied by a shift in the rate at which the star slows. This suggests that the magnetosphere itself can reorganize. The field is not a fixed cage. It is a moving plasma system tied to a conducting star. At higher magnetic strengths, a different kind of neutron star appears. The name magnetar is used for objects whose observed behavior is powered mainly by the decay and rearrangement of an unusually strong magnetic field rather than by rotation alone. They often rotate more slowly than ordinary radio pulsars, yet their X-ray output can exceed what their spin-down energy could supply. The energy must come from elsewhere. It comes from the field. A magnetic field stores energy. In a magnetar, that stored energy is immense. The interior field may be stronger than the surface field inferred from timing, and it can twist the crust from within. As the field evolves, stress builds in the solid layers. The crust can shift. Currents in the magnetosphere can change. X-rays brighten, and short bursts may follow. The event is sometimes described as a starquake, though the comparison is incomplete. An earthquake is driven by the movement of rock under forces in a planetary crust. A magnetar outburst involves a dense nuclear lattice, magnetic stress, and plasma outside the star. The motions may be small in distance, while large in energy. Most bursts are brief. Some last only a fraction of a second. Others continue longer or occur in clusters over days and weeks. A magnetar can remain relatively quiet for years, then enter an active period. Its surface temperature may rise, the pulse profile may change. The rate of rotation can shift as the magnetosphere rearranges. A few events are far larger. Giant flares have released intense gamma radiation in less than a second, followed by a fading tail modulated by the star's rotation. Only a small number have been recorded in the Milky Way and nearby galaxies. Their rarity leaves uncertainty about the full range of magnetar behavior. The strongest fields alter matter and light near the surface. Atoms become stretched along magnetic lines. Electrons move more freely in one direction than another. The vacuum itself responds through quantum effects, changing the polarization of passing radiation. These conditions follow from familiar particles placed inside a field far beyond terrestrial experience. A magnetar does not strip apart every distant object by default. The effect depends on distance, field strength, and the material involved. Far from the surface, the field weakens rapidly. Near the star, however, atomic structure and radiation transport can differ sharply from ordinary conditions. The field reaches outward, but its grip is not infinite. Simple descriptions often define magnetars only by danger. Their scientific value lies in how they connect dense matter, powerful fields, quantum effects, crustal stress, and high-energy radiation. They are difficult to classify cleanly. Some neutron stars behave like ordinary radio pulsars for years and later show magnetar-like bursts. Some magnetars emit radio pulses after an outburst. The boundary between the two groups is not absolute. Rotation and magnetic energy can both contribute, with one becoming more visible than the other at different times. This has led to a broader picture. Pulsars and magnetars may occupy different regions of a continuous population shaped by birth field, rotation, age, crustal structure, and environment. The youngest objects can begin with strong fields and rapid spin. Over time, the spin slows. The field may decay or move through the crust. Thermal energy fades. Emission changes. Some become quiet enough to disappear from current surveys. The galaxy may contain many neutron stars that no longer announce themselves. They drift through space as dark, cooling remnants. Their radio beams may miss Earth. Their surfaces may be too faint in X-rays. Their magnetic fields may have weakened, and their rotation may have slowed. The visible pulsars are only the portions still able and aligned to send measurable signals. That fact returns the story to selection. Astronomy does not observe every neutron star equally. It observes those that speak through radiation, orbit, heat, or gravity. A pulsar is found because its beam crosses Earth. A magnetar is found because it brightens or bursts. A binary neutron star is found because a companion reveals its mass or because the pair begins to merge. Even among detected objects, The classification depends on what is happening during the years of observation. A quiet magnetar may resemble an ordinary X-ray source. A pulsar between emission states may disappear from a survey. The star remains. The signal changes. Rotation is the thread connecting these forms. It carries the magnetic poles across the sky. It organizes the pulse. It stores energy. It reveals motion inside the crust when a glitch occurs. It allows accretion to build a millisecond pulsar and lets timing experiments measure gravity with great care. Magnetism is the second thread. It guides particles, heats the surface, shapes the atmosphere, stores stress, and controls how the star loses angular momentum. In magnetars, it dominates the observed behavior. In ordinary pulsars, it still determines where and how radiation leaves. Neither thread stays unchanged forever. A neutron star spends rotational energy. Its field evolves. The interior cools. The crust responds. The signal that once arrived 30 times each second may slow over centuries. A burst may alter the pulse profile. A companion may return lost speed through accretion. The star keeps changing while appearing almost fixed in size. From Earth, the change is read in time. One pulse arrives slightly later than expected. Another carries a different shape. A burst appears in X-rays. A radio signal returns after months of silence. Across years of observation, these small departures build a record of the star's outer field and hidden interior. The neutron star does not need a visible landscape. Its landscape is temporal. Peaks, delays, glitches, drifts, and recoveries replace mountains and oceans. The pulse train becomes a moving surface, written in seconds. It shows rotation where no disk can be resolved. The voice introduced at the beginning of this section is not a sound. Space carries no ordinary sound between the stars. It is a pattern of radiation, converted by instruments into data and sometimes into audio for human listening. The rhythm belongs to the star. The sound belongs to the method of display. Still, the rhythm is real. It crosses the galaxy without needing air. It survives dust that would block visible light. It records the turning of a body only kilometers wide and older than human history. In some systems, it remains steady enough to test gravity. In others, it breaks just enough to reveal the motion beneath the crust. Not every neutron star remains alone. Some are born with companions that survive the explosions. Some gain matter. Some are spun up. A smaller number orbit another neutron star, each compact remnant carrying its own mass, field, and history. For a long time, such a pair can appear stable. The pulses trace the orbit. The orbit loses energy. The distance shrinks by an amount too small to notice in a single night but measurable across years. Gravity carries the lost energy away in waves, and the two stars begin a long inward path. The clocks start moving toward one another. The clocks start moving toward one another. A binary neutron star system may begin long before either neutron star exists. Two massive stars form from the same cloud and spend their early lives circling a shared center of mass. They burn at different rates because their masses are not identical. The heavier star usually evolves first, expands, loses material, and eventually collapses. If the system survives that first supernova, the orbit changes. Mass has been thrown away. The newborn neutron star may receive a kick from the uneven explosion. The companion may continue on a wider, more eccentric path, or the pair may separate completely. Only some systems remain bound. Those that do enter a second stage shaped by mass transfer, stellar winds, and the slow aging of the surviving star. The companion then reaches its own collapse. A second supernova removes more mass and may deliver another kick. Again, the system can break apart. Again, some pairs remain. The result is rare compared with the number of ordinary stars. But the galaxy is large and old enough for rare outcomes to occur many times. Two neutron stars are left in orbit. At first, the distance between them can be millions of kilometers. Each star is only about the width of a city, yet both carry masses comparable to the Sunday. Their orbit may take hours. The space between them appears empty, but the system is never truly isolated. The stars curve the space-time around them, and their motion changes that curvature from moment to moment. The changing curvature travels outward as gravitational waves. These are not waves moving through a material medium. They are changes in the geometry of space-time itself, spreading at the speed of light. Far from the binary, the effect is extremely small. Distances are stretched in one direction and compressed in another. Then the pattern reverses. The waves carry energy away. The amount lost during one orbit can be tiny, but the loss repeats. The stars move slightly closer together. A tighter orbit makes them move faster, and the faster motion produces stronger waves. Stronger waves remove energy more quickly. The process feeds itself, though for most of the binary's life it proceeds with almost no urgency. Millions of years can pass this way. The system appears stable on human timescales. A pulsar in the pair may send regular radio pulses toward Earth, allowing astronomers to track the orbit with unusual precision. The pulse arrival times shift as the pulsar moves toward and away from the solar system. From those shifts, the masses, orbital shape, and rate of decay can be measured. This was how the first strong indirect evidence for gravitational waves appeared. The Hulse-Taylor binary pulsar, discovered in the 1970s, contains a pulsar orbiting another neutron star. Its orbital period becomes shorter by a small amount each year. The measured change matches the energy loss predicted by general relativity with great accuracy. The stars do not need to be seen merging for the decay to be real. Their clock reveals it. A pulse that arrives a little earlier, after years of observation, shows that the orbit has tightened. The change is gradual enough to hide inside ordinary life, yet persistent enough to alter the future of the system. Gravity is not holding the pair in a permanent circle. It is guiding them inward. The orbit is usually not perfectly circular at first. Supernova kicks can leave it eccentric, so the stars move closer at one part of the orbit and farther apart at another. Gravitational radiation slowly reduces that eccentricity. By the time the stars reach the final minutes before merger, many systems have nearly circular orbits. The long history is smoothed into a rapid spiral. Before that happens, the neutron stars may continue to age. Their surfaces cool, their magnetic fields evolve. A pulsar beam may stop crossing Earth. One member may have been spun up by earlier mass transfer and may continue rotating quickly. The other may remain quiet. The binary can therefore exist without announcing itself clearly. Some are discovered through radio timing. Others remain unseen until the final moments, when their gravitational waves grow strong enough to reach detectors across intergalactic distances. The merger becomes visible only after billions of years of silence. The distance between the stars continues to shrink. When the orbit takes minutes rather than hours, the velocity is already high. The stars circle a point between them, each one distorting the other through gravity. Their shapes are no longer perfectly spherical. Tidal forces pull the near sides more strongly than the far sides. The deformation remains small at first. A neutron star is difficult to stretch. Its gravity is strong, and dense matter resists compression. Yet the companion's field becomes more intense with every orbit. The amount of deformation depends on the radius and the interior equation of state. A larger star is easier to distort. A more compact star yields less. The final waves carry this information. As the stars spiral inward, the frequency of the gravitational signal rises. The amplitude rises as well. The waveform resembles a chirp when converted into sound, low and slow at first, then rapidly climbing in pitch. The audible version is only a translation. No air vibrates in interstellar space. The detectors measure changes in the lengths of perpendicular arms as a wave passes through Earth. Mirrors separated by kilometers shift relative to one another by a distance far smaller than the width of a proton. Laser light records the difference. The signal begins below ordinary hearing and passes through the sensitive range of the instruments. For a neutron-star binary, it can remain visible in detector data longer than the signal from a pair of heavier black holes, because the lower masses allow the inspiral to unfold more slowly. Each orbit adds another cycle. The accumulated pattern makes precise measurement possible. Masses influence how quickly the frequency rises. Spin alters the phase. Tidal deformation becomes important near the end. The distance affects the observed strength. The waveform is not a simple note. It is a record of the entire system compressed into changing frequency and amplitude. The stars are still separate during most of the signal. Their surfaces remain distinct while gravity carries them around faster and faster. The orbital period falls from seconds to fractions of a second. Centrifugal motion and gravity remain balanced only for another moment. The gap narrows. Around each star, the magnetic field is swept through the changing geometry. Plasma may fill parts of the system. The fields can reconnect and release energy before contact, though the details are uncertain, and not every merger produces a detectable electromagnetic precursor. The gravitational signal remains the clearest guide. Near the final orbits, the stars move at a significant fraction of the speed of light. Their combined gravity bends space-time so strongly that Newtonian descriptions are no longer enough. General relativity governs the phase of the motion. Still, the path is smooth. There is no pause before the last orbit. No boundary announces that the long inspiral has entered its final second. The frequency simply continues to rise. The circles become tighter. The time between them becomes shorter. Matter begins to move. Tidal forces raise bulges. The crust may fracture under strain, though whether such fractures create observable signals remains under study. The surfaces remain separated by only tens of kilometers. A distance that once held two stars apart now holds almost nothing. The system has changed scale without changing its components. For millions of years, two objects no larger than cities have orbited across distances measured in millions of kilometers. Now they move within the width of a large region on Earth, carrying more than twice the Sun's mass. Gravity has concentrated the history of the binary into a tiny volume. The final approach depends on the masses and spins. If one star is significantly heavier, it may distort the lighter one more strongly. If both masses are similar, the tidal effects can be more balanced. Rotation aligned with the orbit can delay contact slightly. Rotation opposed to it can alter the dynamics in another way. The interior matters again. A stiff equation of state produces larger stars that touch earlier in the inspiral. A softer equation of state produces smaller stars that orbit closer before contact. The gravitational waveform shifts accordingly. The same hidden pressure that determines the radius now influences the last milliseconds. That connection links the quiet core to the motion of the entire binary. Neutrons, protons, and possible exotic particles affect how the star deforms. The deformation affects the wave. The wave crosses the universe and reaches a detector. Matter hidden under a kilometer of crust changes a signal measured on Earth. As the frequency climbs, the orbit becomes too rapid for any human-scale comparison to remain comfortable. The stars can complete hundreds of circuits each second. Their motion is not random. It follows a waveform whose phase can be predicted until the models reach the point where matter collides and fluid dynamics becomes dominant. The inspiral ends at contact. But contact is not a single clean impact between rigid surfaces. Neutron stars are dense fluids, wrapped in crusts, moving through severe gravity. When the outer layers touch, they shear, compress, and form tidal streams. The boundaries deform faster than an ordinary material could respond. The pair becomes one unstable object. Before reaching that moment, the gravitational waves have already carried away part of the system's mass energy. More will leave during merger. Some matter may be thrown outward. Some may remain in orbit as a disk. Some may fall into the central remnant. The immediate result depends on the total mass. If the combined mass is high enough, collapse to a black hole may happen almost at once. If it is lower, a massive neutron star can survive briefly, or perhaps for much longer. Rapid rotation and thermal pressure can support it temporarily beyond the mass of an ordinary stable neutron star. The categories are provisional. A hypermassive neutron star is supported in part by differential rotation, with different layers turning at different rates. As that rotation becomes more uniform and energy is lost, collapse may follow. A supermassive neutron star is supported by rapid but more uniform rotation and may survive until spin-down removes that support. The lifetime can range from milliseconds to much longer. This hidden interval matters because it affects the amount of material escaping from the system, the shape of the outflow, the strength of any jet, and the light that follows. Yet the central remnant may be obscured by dense matter, making its exact fate difficult to determine. The inspiral itself is easier to read than the aftermath. Before contact, gravity writes a clean pattern. After contact, the signal becomes more complicated. Matter, turbulence, magnetic fields, neutrino emission, and possible collapse interact at once. Models must follow general relativity and nuclear physics together. The last orbit is therefore both an ending and a boundary between two kinds of knowledge. On one side lies a long, orderly decay measured through timing and wave phase. On the other lies a short, dense event, whose details depend on the uncertain behavior of matter at extreme density. The binary has spent most of its existence approaching this boundary. It begins as two massive stars. It survives two supernovae. It may spend hundreds of millions or billions of years losing orbital energy. Its final inspiral enters a detector's sensitive band for only minutes. The ratio is difficult to hold in mind. A process lasting longer than recorded human history by many orders of magnitude announces its ending in less time than an ordinary conversation. The information is not lost. The final minutes contain the accumulated consequences of the entire orbit. The stars move inward because the waves carry energy outward. That simple exchange governs the path. There is no friction from gas required. The space around them can be almost empty. The orbit still decays because the geometry changes, and the changing geometry transports energy away. The process is gentle in description and exact in effect. Each lost fraction of energy reduces the separation. Each reduction raises the orbital frequency. Each rise strengthens the radiation. The system draws itself toward contact through its own motion. No external hand is needed. One system makes this slow geometry especially clear. The double pulsar contains two neutron stars, and both were observed as pulsars when the system was first studied. Their orbit lasts less than 3 hours. The line of sight, the pulse shapes, and the orbit all change under relativistic effects that can be measured over time. The system is not close to merger on a human schedule, but its motion provides a long rehearsal of the same physics that governs the final inspiral. The orbit also turns in space. The point of closest approach shifts. The pulse beams change direction through geodetic precession, a slow turning caused by curved space-time. One pulsar has already faded from view as its beam moved away from Earth, though models suggest it may return in the future. The star has not stopped pulsing. The geometry has changed. This is another reminder that a binary can hide while continuing to evolve. A signal can disappear without the source becoming quiet. The inward motion continues, whether the beam reaches Earth or not. The final seconds become measurable across vast distance because the waves grow strong enough. A detector on Earth may record a pattern that began in a galaxy whose light has traveled for more than 100 million years. By the time the wave arrives, the source has long since changed. The neutron stars may already be gone. The signal is an old movement reaching the present. This delay is true for every astronomical observation, but gravitational waves make it especially clear. The detector does not watch the stars as they are now. It receives the shape of an event preserved in space-time. The binary's clocks have completed their approach. The pulses, if either beam points toward Earth, speed through the orbit. The gravitational chirp rises. The surfaces distort. The last gap closes. For an instant, two stars still exist. Then the distinction between them begins to disappear. On the 17th of August, 2017, a change passes through Earth that no eye can see. It reaches two long laser instruments in the United States and a third detector in Italy. The change is smaller than an atomic nucleus across the length of each instrument, yet its pattern has traveled for about 130 million years. It is the final inward motion of two neutron stars, preserved as a ripple in space-time. The signal receives the name GW170817. For nearly 100 seconds, the detectors follow the rising frequency of the orbit. The early part is slow enough to remain in the sensitive band longer than the brief signals previously recorded from heavier black hole mergers. Cycle after cycle accumulates. The waveform carries the combined influence of the two masses as they move closer together. Near the end, the frequency climbs quickly. The Livingston detector records the signal first, though a brief instrumental disturbance overlaps part of the data. The Hanford detector records it clearly. Virgo, operating in Europe, sees very little even though the event is strong enough to be present. That near absence is useful. A gravitational wave detector responds differently depending on the direction from which a wave arrives. Virgo lies close to a blind direction for this event, helping narrow the region of sky where the source must be. The source is still spread across an area containing many galaxies. Gravitational waves give a distance and a broad direction, but not yet a bright point. The detectors have felt the motion of the binary without seeing the place where it occurred. The event exists first as timing, phase, and strain. Then, another messenger arrives. About 1.7 seconds after the estimated merger time, NASA's Fermi Gamma Ray Space Telescope detects a short burst of gamma rays. ESA's Integral Observatory records it as well. The burst lasts only a few seconds and is weaker than many short gamma ray bursts seen from comparable distances, but its timing places it beside the gravitational signal. Two forms of information have crossed the same distance by different means. One is a change in space-time. The other is electromagnetic radiation. Their arrival times differ only slightly after a journey of more than 100 million years. This places strong limits on any difference between the speed of gravity and the speed of light. It also links at least some short gamma-ray bursts with neutron-star mergers, an origin proposed long before this event but never connected so directly to a gravitational wave source. The gamma rays do not identify the host galaxy on their own. Their direction is too broad. Across several observatories, automated notices begin moving through networks built for this purpose. Telescopes receive the estimated region, daylight, weather, and the position of the source limit, which instruments can respond. The source lies in the southern sky. Hours after the merger, optical telescopes find a new point of light near NGC 4993, an old-looking galaxy in the constellation Hydra. Archival images show no object there before. The new source sits away from the bright galactic center, making it easier to separate from the surrounding starlight. The gravitational distance and the distance of NGC 4993 agree. A location has emerged. This is the beginning of multi-messenger observation for a neutron-star merger. The phrase describes a simple idea. The same event is studied through more than one carrier of information. Light is not one messenger, but a family of them. Gamma rays, X-rays, ultraviolet light, visible light, infrared radiation, and radio waves belong to the same electromagnetic spectrum, yet each responds to different temperatures, particles, and regions of the outflow. Gravitational waves add something different. They come from the bulk movement of mass itself. The event is therefore not observed once. It is observed in layers. The gravitational waveform describes the approach. It constrains the masses and shows that the objects fall within the range expected for neutron stars. It also records the way their bodies respond to tides during the final orbits, though the measurement is not precise enough to select a single interior model. The gamma-ray burst marks a fast release of high-energy radiation after merger. Visible and infrared light follow the expanding matter thrown from the system. X-rays and radio waves appear later, as a narrow outflow interacts with surrounding gas. Each signal begins at a different time and fades along a different path. The optical source changes quickly. During the first night, it appears blue and hot. Over the following days, it becomes redder and shifts toward infrared wavelengths. The light does not follow the behavior of an ordinary supernova. It fades more rapidly, and its color evolution points toward expanding material whose opacity changes as newly formed nuclei decay. This transient is called a kilonova. The name refers to an event brighter than a typical nova but generally dimmer than a supernova. It does not mean the light has one fixed brightness. The appearance depends on the amount, speed, composition, and geometry of the ejected material, as well as the viewing angle. In GW170817, more than one outflow likely contributes. Some matter is pulled outward by tidal forces during the merger. Some is heated and pushed from the contact region. Additional material may leave a disk surrounding the remnant during the seconds that follow. These components do not all contain the same proportion of neutrons, and they do not all produce the same elements. The early blue light suggests material with lower opacity, allowing radiation to escape relatively quickly. The later red and infrared emission points toward matter containing heavier R-process elements, including lanthanides, whose many atomic transitions trap light and release it more slowly at longer wavelengths. The color is a measure of hidden chemistry. No telescope sees individual gold or platinum atoms in the first images. The evidence comes from the overall light curve, spectra, theoretical nuclear calculations, and the way opacity changes when heavy nuclei are present. The event supports the idea that neutron-star mergers create a substantial amount of R-process material, though the exact yields of individual elements remain model-dependent. That slower chemical story belongs to the next part. For now, the light is still changing. Ultraviolet emission fades quickly as the outer layers expand and cool. Visible wavelengths decline. Infrared light persists longer. Spectra are broad and difficult to read because the material moves at a large fraction of the speed of light, smearing individual atomic features across wide ranges of wavelength. Ordinary stellar spectroscopy often identifies elements through narrow lines. Here, the expansion blends them. The absence of clean features does not mean the material is simple. It means the outflow is moving too quickly and contains atoms with complex electron structures. The merger is visible, but not transparent. X-rays do not appear immediately. NASA's Chandra X-ray Observatory looks at the source during the first days and initially finds no clear emission. Later observations detect a rising X-ray signal. Radio telescopes follow a similar delayed increase. This delay helps describe the geometry. A narrow jet of material is launched at nearly the speed of light, but it is not directed straight toward Earth. At first, its brightest emission is beamed elsewhere. As the jet slows and interacts with surrounding gas, the cone of radiation widens into the line of sight. X-rays and radio waves rise gradually, peak, and then fade. The result differs from the simple picture of a uniform explosion spreading equally in every direction. The merger ejects matter in several forms. A broad cocoon of heated material surrounds a narrower, faster jet. Slower kilonova debris expands more widely. Each structure carries a different amount of energy and produces light by a different process. One event contains several clocks. The gravitational chirp lasts roughly 2 minutes in the detector band. The gamma-ray burst lasts seconds. The optical color changes over days. The X-ray and radio afterglow develops across months and remains detectable much later. Combining them resembles learning about an unseen object through sound, color, and temperature at the same time. The comparison is imperfect because gravitational waves are not sound and electromagnetic wavelengths are not separate human senses. Still, each channel responds to a different part of the physical event. No single one gives the complete shape. The gravitational waves reveal the motion before contact. Gamma rays suggest the formation of a relativistic outflow. The kilonova reveals heated, neutron-rich debris. Radio and X-ray observations trace the jet as it moves into its surroundings. The host galaxy provides age, location, and distance. Together, the measurements turn a brief merger into a long observation. They also offer a new way to estimate the expansion of the universe. Gravitational waves provide a direct measure of distance from the amplitude and form of the signal. The host galaxy provides a redshift, showing how cosmic expansion has stretched its light. Comparing the two gives an estimate of the Hubble constant. The first estimate from GW 170817 is not precise enough to settle differences between other methods. Its uncertainty is large because the viewing angle is not known perfectly, and the nearby host galaxy has its own motion. The method does not rely on the same ladder of astronomical distances used by many traditional measurements. Future events can narrow the range. GW 170817 also compares the travel of gravity and light. The small delay between the gravitational signal and gamma rays includes processes at the source, so it cannot be treated as a pure timing race. Yet, after such a long journey, the near-simultaneous arrival shows that the propagation speeds are extraordinarily close. The event tests physics while revealing astronomy. It does not answer every question. The fate of the central remnant remains uncertain. The combined mass is greater than that of most known neutron stars. Immediately after merger, heat and rapid differential rotation can support an object that would not remain stable as a cold, slowly rotating star. It may survive briefly as a hypermassive neutron star before collapsing into a black hole. It may persist longer under some models. No post-merger gravitational signal is detected strongly enough to decide. The gamma ray burst and kilonova place constraints, but they do not provide a single timeline for collapse. A long-lived remnant could inject more energy into the ejecta than many models allow. An almost immediate collapse may struggle to produce some observed outflow. The exact duration is still being studied. The central object remains behind matter, moving outward. Direct sight is blocked. The strongest post-merger gravitational waves would occur at frequencies where the detectors of 2017 are less sensitive. The event therefore becomes clearer around the center than at the center itself. This is an honest limit. The in-spiral is measured well. The electromagnetic counterpart is observed across the spectrum. The remnant's final identity is inferred rather than seen. A black hole may now remain in NGC 4993 where the two neutron stars met. Around it, much of the temporary disk has fallen inward or escaped. The jet has expanded and slowed. The kilonova debris has cooled until it no longer produces a bright transient. Heavy nuclei continue through their decay chains, though the visible display has ended. The event does not disappear from the data. Its signals remain stored in detector records and telescope images. Researchers return with improved models and revised atomic data. Late X-rays can reopen questions about the jet or central remnant. Better opacity calculations can change estimates of ejecta mass. The observation remains fixed, while interpretation becomes more careful. No earlier neutron-star merger had been followed in this way. There were short gamma-ray bursts before it. There were suspected kilonovae. There were gravitational wave detections from black hole mergers. GW 170817 joins these separate paths in one source. Gravity gives an alert. Gamma rays arrive almost beside it. Visible light marks a galaxy. Infrared radiation follows new nuclei cooling. Radio waves and X-rays trace a jet from the side. The event becomes less like a distant flash and more like an object moving through several physical stages. This changes how future searches are organized. Gravitational wave detectors can identify a merger and send its possible location to telescopes. Wide-field surveys can search for a fading optical source. Spectrographs can follow the color. Radio and X-ray instruments can return later, after the first light has weakened. The coordination must move quickly, because the blue component can fade within a day. The slow parts require patience. A telescope that sees nothing in the first week may detect the afterglow later. An instrument that misses the initial gamma rays may still measure the kilonova. Different observatories do not duplicate one another. They fill different intervals. The 17th of August becomes a date attached to an event, but the merger itself occurred long before the date existed on Earth. The waves and light cross intergalactic space together while life changes on this planet. Only at the end of their journey do detectors, satellites, and telescopes happen to be ready. The timing is accidental. The preparation is not. Decades of work build interferometers sensitive enough to measure space-time strain. Gamma-ray satellites watch large portions of the sky. Optical surveys compare new images with old ones. Communication networks connect observatories in different countries and at different wavelengths. The source is natural. The view of it is collective. No instrument holds the whole event. A gravitational wave detector cannot identify the elements in the ejecta. An optical telescope cannot measure the inspiral phase directly. A gamma-ray satellite cannot map the long radio afterglow. Understanding comes from placing the signals beside one another, without forcing them into a single kind of observation. The merger is both heard and seen only as metaphor. In physical terms, it is measured through geometry and radiation. The geometry arrives first. The radiation follows. Days later, the color reddens. Months later, the afterglow rises. Years later, the same data continue to constrain the matter inside neutron stars and the expansion between galaxies. The event stretches through time even though the merger itself is brief. By the end of the observations, the two original stars cannot be separated. Their identities have been replaced by a central remnant, an expanding cloud, a jet, and a set of waves already passing beyond Earth into more distant space. What remains nearby is matter. It carries excess neutrons away from the point of contact. It cools through radioactive decay. It changes color as light moves through atoms that did not exist before the merger. Gravity has finished drawing the stars together. Chemistry is beginning in the material left behind. Chemistry is beginning in the material left behind. The first atoms do not appear fully formed in a single instant. The merger throws out matter so rich in neutrons that ordinary nuclear pathways no longer describe what happens. Atomic nuclei are struck again and again by free neutrons, often faster than they can decay. They grow heavier in hurried steps, moving far beyond the stable elements found naturally in most stars. This is the rapid neutron capture process, usually shortened to the R process. The name refers to speed at the scale of the nucleus. A neutron is absorbed. Another follows, then another. The nucleus becomes so heavy and so crowded with neutrons that it moves far from stability. Only after the supply begins to thin do many of these nuclei decay back toward more lasting forms, changing neutrons into protons and releasing energy along the way. That released energy keeps the expanding debris warm. The kilonova does not shine because a central flame is burning. Its light is powered largely by the radioactive decay of newly created nuclei. Countless unstable atoms are settling toward more stable arrangements, each one adding a small amount of heat to matter already racing away from the merger. The glow is chemistry in motion. At first, some ejecta can remain relatively poor in the heaviest R-process nuclei. Neutrinos from the hot remnant and surrounding disk may change part of the neutron population into protons, altering which elements can form. This material can produce lighter R-process species and allow blue or ultraviolet light to escape more readily. Other outflows remain more neutron-rich. There, the nuclear pathway reaches heavier elements, including the lanthanides. These atoms possess complex electron structures with an enormous number of possible transitions. Light moving through such material is absorbed and re-emitted many times. The ejecta becomes less transparent, and the energy leaves more slowly at red and infrared wavelengths. A color change follows. The early blue light fades. Redder emission grows more important. The shift is not merely the cooling of a hot cloud, though cooling contributes. It also records the changing opacity of matter, whose atomic structure did not exist before the two neutron stars merged. The color carries composition without displaying a clean list of elements. In rapidly expanding debris, spectral features are broadened and blended. The outflow moves at a substantial fraction of the speed of light, so radiation from one region is shifted differently from radiation leaving another. The many transitions of heavy atoms overlap. A spectrum that might appear crowded with narrow lines in a quiet laboratory becomes a wide and uneven surface. Identifying individual elements is therefore difficult. The strongest early evidence from GW 170817 came from the combined brightness, color, and timing of the kilonova, rather than from a simple fingerprint of gold or platinum. Models containing R-process material reproduced the broad movement from blue to red and the speed at which the source faded. Later observations of another kilonova, associated with a gamma-ray burst, provided a more direct spectral indication of tellurium, showing that at least some mergers can form identifiable heavy nuclei across a broad mass range. Tellurium is not the final destination of the process. The same neutron-rich conditions can create nuclei that eventually decay into elements such as silver, gold, platinum, and others near the heavy end of the periodic table. Their exact proportions depend on the neutron richness, expansion speed, entropy, neutrino exposure, and lifetime of the remnant. There is no single stream of identical material. Some matter is torn away during the final orbit by tidal forces. Some is squeezed and heated where the stellar surfaces meet. Some escapes later from the disk around the central remnant. Magnetic fields, neutrinos, turbulence, and radioactive heating all influence these flows. The merger continues after contact through its outflows. This changes the common picture of heavy elements being created only in the instant of collision. The moment when the two stars touch is important, but nucleosynthesis also proceeds in matter, leaving the system over the following milliseconds and seconds. Disk winds can carry a large share of the ejected mass, and their composition may differ from the material removed dynamically during merger. The central remnant helps decide what leaves. If a massive neutron star survives for a short time, its neutrino emission can alter the proton-to-neutron balance in nearby matter. If collapse to a black hole happens quickly, the neutrino environment changes. The mass of the disk, the strength of its magnetic field, and the rate at which matter falls inward also shape the final mixture. The elements are linked to an object that may no longer exist. By the time the kilonova is observed, the temporary neutron star may already have collapsed. Its brief lifetime can still remain written into the color and amount of the ejecta. Matter escaping before collapse receives one history. Matter leaving afterward receives another. The evidence is spread through the cloud. This is one reason two kilonovae need not look the same. Viewing angle matters because the outflow is not spherical. Matter near the orbital plane may be more neutron-rich and contain more lanthanides. Material leaving closer to the poles may be changed more strongly by neutrinos and appear bluer. An observer looking from one direction may see a different balance of components than an observer looking from another. The source does not change. The path through its ejecta does. As the cloud expands, radioactive heating weakens. The most short-lived nuclei decay first. Others continue over longer periods. The temperature falls. The light moves farther into the infrared. Eventually, the transient becomes too faint for ordinary follow-up observations. The newly made nuclei remain. They are no longer held by the gravity of the binary if their speed exceeds the escape threshold. They move into the host galaxy, first as part of a hot expanding cloud, and later as individual atoms mixed with older interstellar material. The original shape of the merger disappears. Its chemistry travels on. A galaxy is full of this mixing. Supernovae, stellar winds, planetary nebulae, and compact object mergers all return material to interstellar space. Their ejecta meets gas from earlier generations of stars. Shock waves compress some regions and thin others. Dust grains form. Atoms become part of cold molecular clouds. The process is uneven. One region may receive fresh iron from a supernova. Another may be touched by material from a neutron-star merger. The heavy elements are not spread instantly across the whole galaxy. They enter local environments, mix over time, and may become concentrated in some future stars more than in others. Ancient stars preserve this history. Their atmospheres retain much of the chemical composition of the gas from which they formed. Some very old stars contain unusually high amounts of our process elements compared with iron. Their abundance patterns suggest that neutron-rich material entered parts of the early galaxy before many generations of ordinary stellar evolution had passed. This creates a timing question. Binary neutron stars need time to form. Two massive stars must live, collapse, remain bound, and then spiral together. Some systems take billions of years to merge. The early appearance of our process material means that at least some binaries must complete the path much faster, or that other astrophysical events also contribute. The source of every heavy element is not settled by one merger. GW 170817 shows that neutron-star mergers produce our process material. It does not prove that they are the only site. Rare kinds of stellar explosions may also create neutron-rich conditions. Different sources may dominate at different stages of galactic history, or produce different parts of the abundance pattern. The question is no longer whether mergers can contribute. They can. The remaining questions concern how much, how often, how quickly, and in which proportions. The merger rate matters. The average mass of ejecta matters. The diversity of binary masses matters. A rare event that produces a large amount of heavy material can compete with a common event that produces very little. Estimates continue to change as gravitational wave detectors find more systems and as kilonova surveys improve. A single event gives a detailed example. A population gives a history. Future observations may show whether GW 170817 was typical or unusual. Some mergers may collapse too quickly to eject much material. Others may leave larger disks and brighter kilonovae. A neutron star merging with a black hole can also release neutron-rich matter if the star is disrupted outside the black hole's event horizon. If it falls inward whole, little or no kilonova may appear. The black hole's mass and spin then become part of the chemical outcome. Even absence becomes information. A gravitational wave event without detectable light can suggest an unfavorable viewing angle, a distant source, poor observing conditions, prompt swallowing of the neutron star, or a very faint outflow. Several explanations may remain possible until more events are compared. The periodic table grows through many kinds of stellar lives. Hydrogen and most helium come from the early universe. Stars build carbon, oxygen, and many nuclei up to the iron group through fusion. Explosions and neutron-rich environments extend the pattern farther. No single object produces every element in equal measure. The material in a planet is therefore assembled from several histories. Iron in a rocky core may come largely from earlier massive stars. Carbon in living tissue may have passed through lower mass or massive stars. Some gold and platinum may trace neutron star mergers. Other heavy nuclei may have formed in different rare events. The boundaries blur after mixing. An atom carries no label naming its source. Once it enters a molecular cloud, it can join dust, gas, ice, or a new star. Its origin must be inferred statistically from nuclear physics and abundance patterns, rather than read from the atom itself. Still, the path can be imagined. A heavy nucleus forms in expanding merger debris. It decays through several unstable stages until it reaches a long-lived isotope. The surrounding cloud grows wider and cooler. A shock from another star passes through the region. Over millions of years, the atom becomes part of interstellar dust, or gas. The galaxy turns. Spiral structure gathers gas into denser lanes. Gravity draws part of a molecular cloud inward. A new star begins to form, surrounded by a disk. Dust grains collide and stick. Larger bodies emerge. Some remain small. Others grow into planets. The atom enters one of them. It may be locked inside metal deep below a surface. It may remain in a mineral until erosion releases it. It may be melted, refined, and shaped by a civilization that knows nothing of the binary system where it was made. The route is not direct. There is no unbroken stream from one specific kilonova to one specific ring. Galactic mixing removes that certainty. The useful statement is broader. At least part of the heavy R process material present in the solar system was created in neutron-rich events before the Sun formed, and neutron-star mergers are now known to be one of those events. The connection is physical rather than poetic. The nuclei, in precious metals, require conditions that ordinary stellar fusion cannot provide efficiently. A neutron-rich outflow supplies those conditions. Radioactive decay transforms the unstable products. Galactic mixing carries the results into later systems. Human value arrives much later. Gold does not leave the merger as treasure. Platinum has no special status in the expanding cloud. They are nuclei among many others, formed because the balance of neutrons and protons follows certain paths, under pressure, temperature, and time. Rarity on Earth gives them economic meaning. Their cosmic origin gives them age. Before the solar system exists, the material is already old. It may drift for millions or billions of years before entering the cloud that forms the Sunday. The birth of Earth does not create these heavy nuclei. It gathers them. Planet formation separates them again. Dense metals tend to sink toward the interior of a young molten world. Much of Earth's original supply of gold and platinum moves toward the core. Material later delivered by impacts may add more to the mantle and crust, though the proportions and timing remain subjects of study. The atoms continue changing location without changing identity. Some become part of ore deposits through geological processes. Water, heat, pressure, and moving crust concentrate them. Mining brings them to the surface. Refining removes surrounding minerals. A cosmic history becomes a small object held in a hand. The scale has narrowed from 2 stars to 1 atom. The time has stretched from milliseconds of neutron capture to billions of years of travel and rearrangement. That contrast gives the merger a second life. Its gravitational waves pass outward and become too weak to notice. Its light fades, its jet slows. The central remnant grows quiet. The matter continues into the galaxy, carrying the products of those first seconds into environments that did not yet exist. Nothing about the process requires intention. Gravity brings the stars together. Nuclear forces govern the captures. Radioactive decay releases heat. Galactic motion mixes the debris. New gravity gathers it again. The cycle is not closed in a perfect circle. Some matter falls into black holes. Some remains between stars. Some is locked inside long-lived dwarfs. Some enters planets. The galaxy redistributes rather than repeats. A neutron star begins as the compact remainder of one stellar death. A merger turns 2 such remnants into a new remnant and a cloud of fresh nuclei. The material of endings becomes part of later beginnings. The statement is simple, though the path is long. A star burns. Its core collapses. A neutron star remains. 2 remnants orbit. Their motion becomes a wave. Their meeting becomes light. Their debris becomes chemistry. The chemistry enters darkness again. By the time a kilonova has faded, the atoms no longer belong to the event in any visible sense. They are part of the interstellar medium, moving with gas, dust, magnetic fields, and shock fronts. Their creation is finished. Their journey is not. Somewhere in a galaxy, a cloud receives them. The cloud cools. Gravity begins another quiet gathering. The neutron stars are gone, but their matter has not ended. It has only changed where it can go. Beyond the fading debris, space returns to its usual darkness. The last infrared light thins across the distance. The new elements travel without brightness, carried into a future that will unfold too slowly for any single observer to follow. The long journey through the neutron star is nearly complete. Only the quiet remains. The path of that material can be followed only in fragments. A telescope may detect the light of a kilonova for several nights. A spectrograph may record broad features whose meaning is still being refined. A gravitational wave detector may preserve the final orbit in a pattern of changing frequency. After that, the evidence disperses across scales that no single instrument can watch continuously. The atoms move quietly on. Some enter cold clouds by galactic standards. Others remain in hot gas longer. Some settle onto dust grains. Some travel through regions so thin that collisions are rare. Their speed changes as they meet surrounding matter, and the original direction of the merger is gradually lost. The debris stops looking like debris. It becomes part of the ordinary medium between stars, though nothing about its origin was ordinary. A future observer could pass through that region without finding a visible boundary. The cloud would no longer carry the shape of the event. It would carry only a slightly altered chemistry. That chemistry may outlast every image of the merger. Galaxies preserve their history in abundance patterns. The proportion of one element to another can reveal which kinds of stars lived and died before a later generation formed. Iron records one set of processes, carbon records another. Europium, often used as a tracer of the R process, records neutron-rich events that occurred before the star containing it was born. The pattern is never perfectly clean. Gas mixes. Stars move away from their birthplaces. Small galaxies merge into larger ones. Material is stripped, stirred, and gathered again. A chemical signature can remain while the location that created it disappears. Astronomers therefore read populations rather than isolated atoms. They compare old stars with young ones. They study stars in the Milky Way's halo, where ancient populations preserve early conditions. They examine dwarf galaxies, whose slower chemical evolution can make rare events easier to recognize. In some of these systems, several stars share a strong R process enhancement, suggesting that a single powerful event enriched the gas from which they later formed. One event can leave many descendants. The stars do not inherit the merger itself. They inherit material from it. This distinction matters because the universe does not preserve stories in the same way people do. There is no memory stored as an image or a name. There are only consequences: a changed orbit, a new nucleus, a cloud with a different composition, a pulse arriving later than expected. From those consequences, the earlier event is reconstructed. The same method reaches back to neutron stars that are no longer visible. A binary may merge and leave a black hole that emits little light after the surrounding matter is gone. The original stars disappear as separate objects, yet the gravitational waveform remains in an archive, and heavy elements continue through the galaxy. The source becomes inaccessible. Its effects remain measurable. There may be many such mergers that leave no bright counterpart. Some occur too far away. Some are hidden behind dust. Some are viewed from directions that make the jet difficult to detect. Some may produce only faint kilonovae. The absence of light does not mean that no elements were formed. It means the event was not fully observed. Future detectors will find more of them. Improved gravitational wave observatories can measure quieter signals and reach farther into the universe. Better localization will allow telescopes to search smaller regions of sky. Infrared instruments will follow red kilonovae that optical surveys might miss. More complete samples will show how much diversity exists among mergers. Some systems will contain stars with nearly equal masses. Others will not. Some remnants will collapse quickly. Others may remain neutron stars for longer. Some outflows will be rich in lanthanides. Others will contain more material that stays relatively blue. The light curves will vary because the physics varies. The question becomes statistical. How often do mergers occur in a galaxy like the Milky Way? How much R process material does each event eject? How long after star formation do most binaries merge? How efficiently does the material mix? Each answer changes the predicted chemical history. A high merger rate with modest ejecta can produce the same total amount as a lower rate with heavy ejecta. A population dominated by long delay times enriches galaxies later. A small fraction of rapidly merging systems can explain early R process signatures. The solutions must fit more than one kind of evidence. They must agree with gravitational wave detections, kilonova brightness, stellar abundance patterns, nuclear calculations, and models of binary evolution. No single field can settle the matter alone. The story of a gold atom crosses several sciences before it reaches a human hand. Nuclear physics describes the capture and decay pathways. Relativity describes the inspiral. Fluid dynamics follows the collision. Plasma physics shapes the jet and disk. Astronomy measures the light. Galactic evolution carries the material into new stars. Geology concentrates it inside a planet. The object at the end of the path is small. The chain behind it is not. The merger does not make them meaningful. It makes them possible. Meaning is added later, through use, rarity, memory, and culture. The atom itself follows only physical law. It can become part of a circuit, a medical instrument, a ring, or a layer of rock without changing what it is. Most heavy atoms on Earth will never be identified individually. They will remain mixed with other matter, buried in the mantle, dispersed through oceans, or locked inside objects that are never examined. Their origin is shared rather than personal. The connection does not require a specific atom to be traced. It rests on the pattern of the universe. Massive stars form. Some leave neutron stars. A few neutron stars remain paired. Their orbits shrink. Their merger ejects neutron-rich matter. That matter joins later generations of stars and planets. The path is rare at each step, but the universe provides enormous numbers of stars and enormous amounts of time. Rarity becomes enough. A galaxy may wait a long time between nearby mergers. When one occurs, it can distribute a large amount of newly formed material. The enrichment is uneven at first, then gradually diluted and spread. Different stars contain different histories. Even the Sun reflects several sources. Its chemical composition was inherited from a cloud enriched by earlier generations. Those generations did not all live together or die in the same way. Their products met only after long movement through the galaxy. The solar system begins with mixed ancestry. A fragment from one stellar wind joins iron from another explosion. Dust carrying R-process nuclei enters the same rotating disk. Gravity gathers them without preserving their separate roots. Planets form from that loss of distinction. Inside Earth, the materials separate again by density and chemistry. Heavy metals sink. Lighter minerals remain closer to the surface. Later impacts, volcanism, water, and plate movement rearrange the accessible portion. The cosmic mixing becomes geological sorting. Human activity adds another stage. Ore is removed, crushed, heated, dissolved, purified, and shaped. A nucleus formed in neutron-rich ejecta may pass through machines and hands before becoming part of an object small enough to disappear in a pocket. Nothing in its structure reveals the violence of its birth. The atom is stable now. That stability is the final change in a long series. It began far from the valley of stable nuclei, loaded with more neutrons than it could keep. Decay moved it through several identities. Each step released particles and energy. Eventually, the transformation stopped. The result could wait almost indefinitely. It could survive the formation of a star, the cooling of a planet, and the rise of life. The merger's light lasted days. The nucleus can last longer than worlds. This reverses the visible importance of the event. The bright part is brief. The quiet product endures. A kilonova draws attention because it changes quickly. Its atoms matter because they do not. Once stable, they become available to the slower universe of clouds, rocks, planets, and living systems. The universe often works this way. A short transition creates a long condition. A collapse lasting less than a second produces a neutron star that can remain for billions of years. A merger lasting moments creates nuclei that can persist through the age of a planetary system. The brief event is not the whole story. Time after the event matters just as much. The expanding debris cools into invisibility. The central remnant becomes quiet. The jet fades into the surrounding gas. What remains joins, processes too slow for a dramatic image. Clouds drift, dust settles, stars form, planets cool. The material continues without needing to be seen. This is where the story begins to lose its sharp edges. The neutron stars are no longer separate. The kilonova is no longer bright. The new elements are no longer new. They have entered the background. The universe keeps them there, mixed with older matter, until gravity gathers them again. The universe keeps them there, mixed with older matter, until gravity gathers them again. For now, the movement can become slower. The neutron stars have completed their long approach. Their pulses no longer need to be followed. The bright cloud has faded into the space around it, and the newly formed atoms are traveling through darkness without sound. Nothing is asking to be remembered. The distances can soften, the names can drift away, the numbers can become less distinct, like points of light disappearing behind a thin cloud. Beyond the room, stars continue to turn at their own pace. Some are burning quietly, some are cooling. Some have already become small, dense remnants moving through parts of the galaxy that no telescope is watching tonight. The body can rest now. Breathing may become slower without effort. The shoulders can loosen. The weight of the head can settle more fully against the pillow. There is no need to follow the matter any farther. It has already traveled enough. From a stellar core to a neutron star, from an orbit to a wave, from a merger to light, from light to elements, from elements to silence. The final glow is growing dimmer. The debris is spreading until no edge can be seen. Far behind it, the galaxy continues its patient rotation, carrying old stars, new clouds, and matter from events that ended long ago. The universe does not hurry. It gathers, changes, and releases. Then it becomes quiet again. Let the last image remain for only a moment. A small cloud moving through black space, its light almost gone, its particles continuing into a future too distant to imagine. Then let that image fade. The room remains still. The night remains open. Nothing more is needed. Is greater than is greater than is greater than.